What is up, YouTube? This is Larry with Critical Care Connection. Yeah, different than before. Sounds a little bit odd, but so now we have a Prince vibe going on where we're formally known as this. So, yes, we used to be Critical Care Academy. Then we decided that we were doing some searching around YouTube and we noticed that we were very closely named with another channel with very similar type content for nursing. We did not want to step on anybody's toes or, a flow of traffic. It was confusing to have two different channels named very similar. So we decided, let's just remake it. And so we went with Critical Care Connection. It flows good. We want to have a connection with you guys, and we want to be able to connect in a way where we can learn and do things pretty seamlessly. So hopefully not too confusing, but at least you know why now the name has changed. So today we're going to be talking about Swan Ganz catheters. I've got some laid out here, and I think it's going to be pretty cool. So let's get into the action and let's start learning about it. All right, guys. Hey, welcome back. So I need your help with something. I looked back through some of my old videos. I thought, well, this information's there. It's good. It's what you need. But it's kind of droning, kind of hard to watch. So my idea this time is let's try to do a little bit more with animations, make a little bit more pop, but yet be very direct and kind of get the information out there without it being so long and lengthy. So I need your help to figure out what you guys like, what kind of content works best for you. So if you could, let me know in the comments, say, this compared to this one, I would prefer to see this. So, and hopefully in doing that, we make some better content from you guys and you will be able to enjoy it more. I'm all about that. So just let me know what you need. So let's get into what we're going to talk about today and have a good time. All right, guys, we're talking about what is a Swan Ganz catheter. So this is a creation by these two guys, Dr. Swan, Dr. Ganz, back in the 70s. Their whole goal when they set out was to create a device that could better determine cardiac outputs. And man, they did a fantastic job because through evolution of time and what we have now, we have a great diagnostic tool to be able to better determine hemodynamic statuses. So these are super helpful in your population of patients that are post-MI, cardiogenic shocks, pulmonary hypertensions. There's on and on uses of this catheter. And it's super simple design, single lumen outside, has 4 or 5 lumens inside, each one of them with their own specific kind of diagnostic portion. So, we couldn't have asked for more from such a simple thing. And being able to shoot cardiac outputs and determine numbers on the fly, what better way to determine whether our interventions for these patients are working. So, huge kudos to these guys. And so let's get into a little bit more about what these are, and we can talk about how to use it. Let's do it. Okay, guys, here's our catheter. So this is kind of an overview of all the pieces and parts of what you'll see and some of what you won't see. So if you look at our catheter here, this kind of wound up piece here, this is all your mostly internal stuff that you're not going to be able to see. But if you'll notice on the end here, it's slightly kind of discolored. This is where your balloon tip is. So if you want to check pulmonary wedge pressures, I'll show you that here in just a minute as the balloon blows up and deflates. So then you have markings along the way here. So these are all measurements of how you're going to be able to say, hey, my catheter's at such and such centimeters, and this is how we kind of keep continuity across our shift changes and through the day, just to make sure that our swan is not moving in place. You'll notice here you have these small little ports that these are kind of your terminal points for each of these guys here. So along the way, just depending on where they sit at, you'll have these little exit points
along the way. So let's say we go down. Each one of these skinny marks that you're going to see are all 10. So you'd have 20, you'd have 30, move along as you'd imagine. 4 is 40. But now we get down here, and now we got this big fat guy right here. What does that mean? So this is 50. So any increment of 50 is going to be shown as this kind of wide marking. So if you move forward to 60, basically, as you would imagine, you would have a big wide mark plus another 10 makes 60. Down more is 70, and so on and so forth. And we'll talk about how to exactly measure here in just a few minutes. Now, so if you look at the rest of this, so you've got, on this particular catheter, you've got 4 infusion ports here, and then this guy right here is actually not an infusion port. It's got a cap and it's got some leads inside. This is actually for thermodilution if you're going to be shooting cardiac output. So it's just used for cardiac output only. So you're kind of looking at these saying, God, what the heck are all these guys? So individually, they all will tell you if you forget along the way. So like you can see on this one, it says PA distal. This one in the blue will tell you, it's kind of hard to see, but it is RA proximal, so right atrial. This one, auxiliary RA proximal. So this one is not exactly a diagnostic tool, but you can run fluids, you can run meds, you can pull blood from this. So this is kind of a freebie line if you need it. And then you'll notice your red one here is connected to a syringe, and it will tell you on there, it'll say balloon cap, and this one is 1.5 cc's max. So one other thing that's nice about this, so if you look at your syringe itself, it's got a indented place here. So if you go to pull back, it should stop right there, and you'll notice it's exactly 1.5. So it's kind of safety net for this, so you don't instill more air in the balloon. So let's take a quick peek at it. So if we do have air in it, this is pretty cool how this does, but you'll instill the air and boom, that's how you wedge. There's the balloon tip, and this is how you would get a pulmonary wedge pressure. So now you can lock this and it will keep the air in it. I don't necessarily see any reason to lock it right now because you really don't want to do this for more than just a very short period of time. Think about this. I mean, this is occluding your pulmonary artery, so you don't want to occlude blood flow for a very long period of time. So once you let go, it should pull all the air back out of itself. Me personally, I will open it just to make sure there's no air trapped in. I will shut this all the way to 0, and I'm going to put it back on there, and I'm actually going to lock it because I don't want anybody coming around by accident or the patient rolling over somehow or messing with it and being able to instill air into it. So that's how that works. Now, let's talk about what you're actually going to see if this was attached to a patient. So there's a couple pieces you're going to notice. So you'll have a sterile sleeve, and this is going to be going over the actual catheter, and we'll look at it. So let's just slide it over the end here. So let's feed it through like so, and we're just going to kind of pull this too for right now. So there's your sterile sleeve, and remember, if you watched our video on TVPs, we talked about introducers and sheaths. Well, this is it. This is the external, kind of an external view of what your sheath looks like. So this one is pretty wide bodied. This is an 8 French sheath. You'll notice it has just an infusion port off the side of it that you could use if you needed. So remember, so once we put an introducer or sheath, let's say this was my right IJ, and they went in and put this sheath in, and there it is. It sits. This is what you're going to see outside of the body. You're not going to see the rest of it inside. But just remember, this is basically a highway to be able to feed stuff in, like this catheter. So this is not, like I said, the right one for this exact catheter, but let's just pretend for a second. So they've got your sheath in. Now we're going to go ahead and advance our Swan in. This one's a little bit on the small side, but just pretend here for a minute. So now let's say they've put your Swan in. Now this cap here specifically, if it was the right one, notice you have these little kind of clefts here. So you would have a nipple on the introducer itself where you would slide this over top, and what you would want to do is you want to twist that nipple over into either one of these sides. That will lock the two of these together. So now you'll have one kind of cohesive piece, and it will stay that way until you get ready to take your Swan out. The next thing I want you to kind of notice on this one, you have a setting right above it now that you've got this on and off. So it may be hard to see on here, but so you can twist this here and it will either lock it. Now you should be able to take your catheter in here, and now it should not be able to move. We should not have any problems with this catheter moving back and forth. It should be locked in place. If it is not, and it's like this, now you notice you have this free movement. This is extremely important when you're getting a patient from the lab. If this is not locked, and you'll also have another one on this end, and it's the same exact way. You've got the same markings, and it's kind of hard to see here, where it will twist and lock and unlock. So you've got basically a circle and a straight line. Circle is open, that's how I think of it, and then once you're over to your line, notice I can't move it, but if I twist it back this way, look how freely it moves. So think about why that's important. You're moving your patient over in the bed. They've got all this stuff wrapped around and done. How easily would it be if this was not locked now to just willy-nilly just kind of pull this back 10 centimeters? I mean, it would be extremely easy. So I always tell people, what I want you to do before you start moving anybody around, make sure both of these are locked, because it will easily prevent something from happening to that catheter and moving it, and then they're going to have to end up coming and repositioning it again. So this is how it's going to look on your patient. Now this sleeve is kind of bunched up. It will extend out quite a bit further than this. Now that you see that your sleeve is extended out, try to get you a view in here. This is how we want to measure this. So remember we said our markings, they're going to be here. You got a big one, which is 50, and two small lines, which are going to be 10 apiece. So with that being said, we're going to take our measuring device, whatever that may be, and we're going to measure right from the inside of this little plastic hub, right on the edge there. We're going to measure across just till we get to the beginning of the fat line there. So we know that with that being said, we've got one big line, two small lines. That's 70. Remember, we got to go backwards. So whatever we measure from here to here now, let's just say it's 6 centimeters. So what we're going to do is we're going to take 70, we're going to minus that 6 centimeters. It's going to give us 64 centimeters, and that's what our Swan is going to measure at. Now if we change that and it was, let's say we pulled a little bit closer now, we straighten our catheter up. Now we say this is, now we have a gap of 4. So basically we're going to take 70 minus 4, and that's going to give us 66 centimeters. So that's what we're going to use each time to measure, and that's what the best way we're going to keep track of position for the Swan. We're going to use that in combination with the use of waveforms, and that will help us best determine the placement of our Swan. The Swan setup. So lots of cords, lots of wires, very intimidating to see the first time. It kind of looks like a bird's nest of stuff. So I think real quick, let's break it down into different pieces. That way it's not as intimidating anymore after you see it all kind of broken down. And I feel confident that anybody could set this up after they see it done. So number one is our normal saline pressure bagged, and it's got a transducer set up to it. So the priming spike goes into the fluid, and then a triple set has 3 ends to it. So like for our use, we're using 3 ends. Now the Swan only uses 2 of these. If you have an arterial line somewhere, you can also set that arterial line on here and make life simple and kind of cluster it all together. If you don't have somebody with an arterial line, you're more than welcome to wrap all the tubing up and kind of tape it together, put it out of your way, and forget about it. But I think having one pressure bag with multiple ports is much easier than having multiple ports and multiple bags. So let's start from there. So we've got our fluid hooked to our transducer. In the real world, the transducer and mount would be hooked to the pole too, but for our sake, I just separated them here because I think it's easier to look at separately. So let's color coordinate everything. So we'll go to our yellow, which is our PA. So we're gonna run this cord. We're gonna run it up and around, and we're gonna hook it straight into the yellow port here. So from there, what we're looking at next is gonna be our blue port. So we're gonna run our blue, which is our RA. We're gonna run it up, around, find our blue here, and hook it in here. Last but not least, we see our arterial. Remember, I said this is optional if you have arterial. If you don't, we're gonna wind it up. For this story, we are. So let's bring our arterial here and around, and not this red line. Remember, you have a red on your Swan. It is not an arterial line. It is solely for the purpose of the syringe to inflate your PA balloon. So, with that being said, let's bypass that and make our way around to our patient, and we'll hook it in right here. So, that's the setup from the bag to the transducer, transducer to the patient. Last piece of this puzzle that we need to make all this work is we need to hook this into the monitor. Now, on the bottom where your fluid came into your transducer, you notice you've got another piece hanging there. Those are connectors for your monitor. So you'll have each individual one. So we need to hook up 3. So what we're gonna do, we're gonna take our first one. This is easier with 2 people because you can have one person saying, here's the PA, and they plug it in. Because each part, depending on your monitor, is gonna have a different input. So let's run our first cord up here, and we'll hook it in. So I've got our PA in. Now when you plug these in, you'd love to see, ideally, PA pop up on your monitor. Now, it could pop up arterial, and that's okay too. We just need to change the name and dedicate it to a PA. So let's do our RA next. We'll bring it up, plug it in here. And then last but not least, your arterial needs to come up and plug in here as well. So now you've got 3 plugs to the patient in the Swan, and then to the arterial line if you have it. And then you've got 3 electrical connections from your transducer up to your monitor. And they're all designated for what they're supposed to be, which is PA, arterial, and RA. So not so bad once you look at it from a distance. So I hope this helps and makes life a little bit easier for you. About Swans and transducing pressures is you always need to make sure that your Swan is level with your patient. Think about all the tasks you do through the day where you're moving, turning, doing care. You know, you're moving the patient all around all the time. So you need to go back and double check that your Swan is actually sitting where it's supposed to be. That way you know that you're transducing an actual accurate number. So what I mean by this, so if you look at the diagram here, you got your transducer, and we've got it level to what's called the phlebostatic axis. So basically, you're making sure that your actual transducer is sitting basically heart level. So why is that important? It's a strong question asked by everybody. So think about rolling a ball up or down the hill. So let's say now we take our transducer and we slide it way up the pole, or it stays the same and maybe you lowered your patient down. So now let's say it's up here. So think about what kind of pressure would it take to get downhill back here. Let's say we had a ball and we had to kind of measure the pressure of how hard it would be to get that ball down there. Well, theoretically all we'd have to do is just kind of give it a little shove and it would go under its own pressure. So it would take very minimal pressure. So that's going to reflect in your blood pressure because it's all based off pressure. So let's say your starting blood pressure was, let's say 120/80, right? Now, if we move this up here, like so, where we had it, now you may be transducing a pressure on the monitor that says, let's say 90/70. Now this may be a little bit extreme, but I want you to see that if this is higher than the patient's level, it's going to show you a lower blood pressure. Now, adverse, let's say your transducer now is way down here, but your patient's way up there. So now you've got this curve to get up here. Same ball. How much force or pressure is it going to take to push it up the hill like this? Well, it's going to take a pretty significant amount of pressure to get uphill. So now we started with that same pressure, 120/80, and now we're way down here at the bottom of the hill. What's it going to look like? Well, it's going to be higher. Let's say now you've got a pressure that reads 140/95. So is the pressure accurate? No, because the transducer is not zeroed to where it should be. But I want you to notice that that makes a pretty significant difference. And when you're working in a tight parameter, whether it be you're titrating your medicines off of your pressures or whatever it may be, you need to know that it's in an accurate place and you're getting accurate numbers. That way you're not making titrations based off these things. So the level is extremely important. So I always, first thing, start off looking at the level and make sure it's in the right spot. And then from there, you can zero things. So in the next part, we're going to look at how to actually zero it once you've got your Swan at your phlebostatic axis. So now you got your transducer, it's leveled out to your patient, and you're in the phlebostatic axis like you're supposed to. So let's talk about how we're going to zero it to make it appropriate and you know your numbers are correct. So first thing you're going to look at is your triple transducer in number 1 here. So notice all the stopcocks are turned to the outside. Now remember, on a stopcock, which way it's pointing is which way it's off. So now this tells you have your pressure is reading from your pressure bag. It's going through the transducer and it's over to the patient side. So it's transducing the patient. So now what we're going to do to zero this thing. So we're going to want to turn all of our stopcocks up to the top position here. So in the picture, you'll see exactly what I'm talking about. Stopcock shoots straight up. So now it is off to the patient side and it's open to the atmosphere. Now, make sure you take your caps off or this won't work at all. So when you take the cap off, you may notice there's a little bit of air or a bubble or two in the actual side port. So if you see that, go ahead and pull your, whether it's pull or squeeze, your flush part to the setup and go ahead and flush a little bit of fluid through there and get the air bubble out. It should only take a drop or two to get it out. So now we're here. So once you do that and you open everything up, you're going to notice on your monitor, and it's all specific to what kind of monitor you have, there's an option to zero. And whether you're zeroing a single line or you're zeroing all, in this case it's easier on a Swan to zero all things at one time versus one at a time. So go ahead and hit 0. You'll notice everything kind of flattens out. So now you just have flat line across the board. You have zeros. Once you see all those and then the word zeroed pops up on your monitor, you know that it's completed. So now basically what we're going to do is put everything in reverse. We're going to take it back. We're going to go ahead and twist all of our stopcocks back off to the atmosphere, and we're going to cap everything just like we had them before. Now, what's that going to mean on our monitor? So we're going to look at our monitor, and what we should have when we do that is going to be a new series of lines, and everything should look pretty good. And what we want to do, as you're seeing that rhythm come across the screen, I want you to flush each port on here
and that's going to do what they call a square wave test. So let's say we have an A line, we have a rhythm here. When you square wave, it's going to come up, flatten off until you let go, return to home, and then prepare your rhythm again. So this is going to show you, make sure that it's not over dampened or under dampened, and it's just checking each one. So like if I squeeze the PA and my arterial line does a square waveform, this also tells you that you could have a problem. So it just kind of ensures that everything's hooked up right and it's hooked up in the right places. So that's all there is to zeroing. Not bad. Once you get the hang of it, it'll take you all of 20 seconds to do it, and you'll ensure that everything is accurate. Waveform dampening real quick. So look at the top one in green. So this is a normal waveform. This is what it's supposed to look like. You've got a square wave with your flush, and then you've got what's called 2 auscultations following your square wave when you let off. And these are kind of like little reverbs before it returns back to baseline. So 2 is considered normal. So if we look at the next one on the bottom left, over dampened. So these I think of over dampened as suppressed, and if you look at it, the waveform looks suppressed and compressed down. So things that cause that: air bubbles, kinks, clots, spasms, stopcocks that are either locked or partially locked more so. But I think most commonly people don't check their pressure bag, and it's most likely got some volume out of the bag, causing not as quite as tight a squeeze as it should. So easy fix there, but that waveform is pretty easy to spot because it's not going to show anything accurate. Your numbers are going to be off. So as you would expect, that waveform is going to produce a lower systolic than normal, and then it's going to show a higher diastolic. So if you do the vice versa and you look at the other side, you've got an under dampened waveform. So this one's kind of sharp and harsh in comparison to the other two, and that's saying that it's not suppressed or compressed enough, and now you've got this high, tall, spiked waveform. So you can see your flush there, and then you can also see as you let off your square wave, you've got several bounces. So this one shows 3 auscultations, and so what we're going to see here, you're going to see an overestimate or a higher systolic pressure than what is accurate, and then it's going to underestimate your diastolic. So just real quick, I just want to show you that because these are quick and easy things that you can diagnose by looking at your monitor and looking at your numbers, and also knowing what your baseline is for your patient. About having a Swan, the fact that you can shoot cardiac outputs, you can see real-time feedback for the treatments that you're giving for these patients. So somebody in cardiogenic shock, you want to see a steady trend in a positive cardiac output normalizing. So that's one way we can check the therapies that we're doing for these people, and we can know that we're making a difference and things are going in the right way. So real quick, let's take a look at the pieces to the cardiac output kit that you'll need. So not every single thing's in it, but it's pretty close, and I'll tell you exactly what you're going to need in order to make this work. So first piece to this that you're going to have that's in the kit itself is going to be this big syringe right here. So that's where you're going to withdraw the fluid to do the cardiac output. So this is in the kit. Excuse me. And it's going to come across here. This is all one piece you're going to have. And then you're going to have this stopcock in the kit itself here. And then there is a little port right here that is going to be a temperature sensing port. And those are the pieces that are going to be a kit. It's going to come with the tubing that goes to your D5 bag that you're going to need. So initially, those are your whole pieces that you're going to have. What you're still going to need to get, you're going to need to get a D5 bag. 500 bag will work. It doesn't need to be in a pressure bag, just a regular D5W bag. And then the other piece to that is going to be a thermometer cord, and it's going to have 2 ends to it. So it'll hook to your monitor, and then it will have an end that hooks here, and there will be another end that connects to your thermistor on this end of the Swan. So we're going to talk about why you have 2 ports here in just a second, but just know you need these things. You need an extra temp cable that is specifically for cardiac outputs with the 2 ends, and you're going to need a bag of D5W. All right, so let's take a quick look at how to set this thing up. So this whole contraption is going to go onto your RA proximal, your blue port on the Swan. So this is going to terminate in the right atrium. So normally you would have this end right here, which is one coming from your Swan setup, your triple transducer. That's one that would be hooked up right here. So the reason we're going to do this way, we're going to take it loose from here. You're going to install your 3-way stopcock here. And then you're going to move your CVP line that you had originally to this. The reason why we're not going to put it over here where the syringe is hooked up is because when you're injecting your D5W, you want this thing to fire straight through. You don't want it to come through and have to turn a 90-degree angle. The CVP line doesn't care. All it's doing is measuring a pressure. So that's the importance of why you set it up straight ahead. So other than that, you've got your stopcock here. Stopcocks are a little tricky sometimes. Just this one is nice because it's labeled off. So when you want to transduce a CVP just like regular, just this position that it's in, it's facing off to the cardiac output syringe. That's exactly what you want just to read a CVP. Now, when we go to do a cardiac output number, what we're going to do, we're going to turn this guy this way. So now it's going to be off to your CVP line. So that way, now it's no number is going to come up on the screen, but now we're going to be able to flush the line with our cardiac output setup. So what we're going to do, in this syringe that's now hooked up to your D5, there is a flapper valve right here. So when I pull back on the syringe, that valve is going to open up and allow me to now put the D5 in that syringe. So you think, well, how does it not go back up into the bag? Well, once you pull it in, that little valve shuts off again, and everything you push out from here is going to go this way. So it's kind of like a full safe kind of thing. So it just flows straight through. You don't have to worry about it back feeding. So now what we want to do, we've got our stopcock turned off here, and then you'll set everything else up on the monitor. Each system's a little bit different. A lot of people ask why D5W. D5W is a little bit more viscous fluid than normal saline, and all these things are taken into account in the measurement of how it's going to create a cardiac output. People think it's a measure of the fluid itself. Only thing that cardiac output's really looking at is this reason right here where you have 2 thermistor or thermometer style ports. So as this fluid comes this way, right past this first sensor, it's going to take a reading and it's going to know exactly what that temperature is. Now remember, we're going into our blue port that terminates in the right atrium. So the next part of the calculation is going to be your other temperature port here. This one, if you're looking at the catheter, when I was showing it to you, on the very end of the catheter that terminates in that PA, that's where your other thermistor sits. So basically you're taking a calculation of time that it takes the fluid, the D5, it's going to go from this thermistor here all the way to the end, and it calculates the time. And it can calculate the viscosity of the D5 and the amount of time it takes for it to reach the other thermistor. And then that's going to calculate how well of a function your heart has now, because it can tell, hey, it took that fluid this long to get from point A to point B, and now I'm going to create a calculation that says this is what your cardiac output is. It's kind of a wild thought, but it's a very simple process at the same time. So hopefully that helps with the understanding of how to set up a cardiac output, and 2, as well as kind of what is it doing to make a number for us. Okay guys, so let's look at this. Waveform identification. Super important piece when you have a swan, because if that swan was to migrate or move, you need to be able to identify that by the waveform.
These changes are pretty dramatic, like you can see on the graph there. They're all different in their own way. So ideally, we were looking for a PA because that's what we want. We want the tip to sit in the pulmonary artery. So if you look at that waveform, it looks very similar to an arterial line. You've got a dichrotic notch. You've got a downsloping diastole. Your numbers, the ideal numbers there are 20 to 30 systolic, over 5 to 15 diastolic. These are going to change per patient, but this is, like I said, this is ideal range. So let's go to the other side. Let's go and look and see. So if it was pulled back all the way to the RA, or if they were floating this in and we're starting in the RA, look at what your waveform looks like there. It's a pretty linear line. It does have some variation up and down, but it's for the most part very straightforward and very straight across. So this is what a waveform of a CVP is going to look like on your monitor. So looking here, your range is 2 to 6. So this would be easy to spot if you saw this on your monitor. The next one, if this got either pulled back into the RV, or if we're kind of working our way through floating one, this is what it would look like. Very tall, very fast, up and down for systolic numbers and diastolic. So your systolic is going to be similar to your PA at 20 to 30, but the big difference, look, all the way at the bottom of diastole is 0 to 5. So that's, besides the waveform, you can look at the numbers to diagnose this. So this is, if it's going to be pulled back, this would be your first stop in being pulled back. So this is a pretty big difference in the two. So I would hope that if you saw the difference in the waveform going from the PA to the RV, that'd be something you would catch pretty quick. Now the last one is pulmonary wedge pressure, sometimes called pulmonary occlusion pressure, either or, that's just a different term. So you'll look at that. When the balloon itself is wedged, it's going to give you a solid number. In somebody with normal heart, normal lungs, your wedge pressure and your diastolic PA pressure should be pretty close to the same. Now, that can change very dramatically depending on if you have a pulmonary issue or a cardiac issue. So if you look at the waveform itself though, it flattens out similar kind of to a CVP, but notice on where diastole would be, it has an upslope to it. So it doesn't go down like the PA does. It has an upslope. So that's one way you can look at that and notice that it's a wedge pressure. The other would be by the range of numbers that it's in. So I hope that's helpful in just kind of looking at the different waveforms for the Swan itself. Now the chart I put beside of it was for a waveform for cardiac outputs, which we talked about earlier. So cardiac outputs work on what? Temperature and time. So as you're flushing that fluid through the catheter itself, it's measuring how long it takes to pass the temperature from that first sensor right beside the syringe to reach all the way to the end of the PA tip. So if you look at the first one, it shows you a normal. So it's a very like steady curve. Like it takes a little bit of time to get to where it starts to rise. And when it rises, it's nice and steady and then has a nice gentle slope down. These are normal. Look at high beside of it. Look how much shorter and taller and skinnier that is. And that's why, because your cardiac output that's high is really churning out the fluid. It's pushing it through there fast. So you've got a shorter amount of time it takes for the fluid to get to the tip, and then it rises sharply because it's all being pushed real fast and it all got there at one time. And then look how fast the downslope is to get back to normal. That's because it's churning out so much blood through there. It came, went, and gone before you can blink an eye. Like it happens so fast, and you can see that in that curve. Now, on the other side of that, look at low cardiac outputs. Somebody that's not really churning out much volume. It takes a long, slow, steady slope up to get the temperature, and then an even longer slope down for it to clear all that fluid
temperature out past the sensor. So when you're doing it on the monitor, you'll see this same slope, and this will kind of help you determine before the number even pops up kind of what you're looking for ahead of time. So I hope all these waveforms are helpful to be able to help diagnose these things.
All right, guys, let's wrap this up. I appreciate you guys coming and hanging out with me while we talk about swans today. I had fun. I hope you guys did too. Leave me some comments about what you like. Did you like more of the animated style stuff, or do you like more of the videos like we've been doing before? It's helpful for me to know how to build the channel. So as always, please go over, subscribe, like the videos. It helps us a ton. If you get time, go check out the store. We've added some shirts. Look like the Sweet Dreams are made of these shirt. We're custom making these shirts, so go get them, go buy them. As always, I'd love to see you next time on the flip side. Alfonso, let's get out of here. Come on.